In this review lesson, we're going to talk about three things. We will first talk about the dimension of vector space and then move on to linear combination. And finally, we'll talk about the span of vectors. Imagine you have a vector v, which is defined as, let's say, vx and vy. These are the two components of this vector. And you have another vector, w, which is defined as, let's say, wx, wy, and wz. In the same way, if someone gives you another vector that is a, and it has n number of elements, for example, ax or a1, a2, a3, in the same manner, it has n components. Now, what you are seeing, basically, all these vectors has a certain number of elements inside it, right? Depending on the number of elements or number of components, we can define vector space. This big R is the set of all real numbers. And then if you add a number on top of it, for example, n, it denotes the dimension of the space. So basically, if you draw two axes, x and y, then that would be a vector space that is denoted by R2. And if you have a three-dimensional space denoted by x, y, z axis, then that would be R3 space. In the same way, if you have a higher dimensions, for example, this one, it has n number of axes. And then you can denote this vector space as Rn. And this would be R3. And this would be R2. And you can symbolically write down vector v is an element of this vector space R2, and w is an element of vector space R3, and a is an element of vector space Rn. Alright? So this is the basic of the vector space. Now let's move on to the topic of linear combination. Imagine we have two vectors, v1, which is 1 and 2, and another vector, v2, which is 3 and 4. Definitely both v1 and v2 have two components inside of it. Definitely we can write down v1 is an element of R2 space, and v2 is also an element of R2 space, right? Because they are two-dimensional vectors. Now, let's suppose we have another vector d, which is defined as, it's an arbitrary vector. For example, let's say 7, and this one is 5. Now the question is, can we express this third vector d in terms of v1 and v2? Can you do that? Is there any way, is there any mathematical way that we can utilize to express this vector d in terms of the given two vectors v1 and v2? And this concept gives the rise to the linear combination. It's a very important topic in linear algebra, and we have direct application of this linear combination in machine learning. So coming back to the original question, can we express this d vector or any arbitrary vector in R2 space? D is also in R2 space, so we can write down d is an element of R2. So in R2 space, can we express d in terms of v1 and v2? This is the original question. And the linear combination is a concept that is derived from this question. So the linear combination is nothing but the sum of the given vectors with proper scaling factors. So C1 and C2 are two scalars, are two constants that are actually operating on V1 and V2 and scaling them. So C1 and C2 could be any constant and this expression is known as the linear combination of v1 and v2. Since we have only two vectors, that's why we have these only two constants, c1 and c2. If we have n number of vectors, we can write down this expression and continue to move on like plus c3 dot v3, and in that way. All right, so this expression is known as the linear combination c1 dot so this is basically vectors v1 and v2, and c1 and c2 are the scalars. So c1 times v1 plus c2 times v2. This is the linear combination of v1 and v2. Now, coming back to the original question, if we replace this linear combination in this original equation, so this part can be replaced by this linear combination of v1 and v2 and can be modified to write d in terms of the linear combination of v1 and c2 times v2. Now, again, coming back to the original point, is there any way to find it? So only unknown d is given. So we have, let me change the color. We have d value, we have v1 and v2. Everything is known. The only unknowns are here c1 and c2. If we can figure them out, then we can satisfy this equation and can express this d vector in terms of v1 and v2. And that is what we are going to do now. So we can write down the equation in this way. So d is given as, so d is given here 7, 5. So according to this equation, we can write down d7, 5. And here we can write down c1 is unknown, so we don't know the value of c1. We are going to figure it out. And v1 is given as 1, 2 plus c2. And v2 is given as 3, 4. If we further simplify this expression, we get, we can actually write it in this way, c1. So this is going to c1 and this is going to 2c1. So this is a matrix 7, 5 plus 3c2, 4c2. And we can write down equations from these matrices. For example, we can write it c1 plus 3c2, c1 plus 3c2. We are adding element by element. So c1, the first element, is added to the first element of the second matrix, and it is equal to the first element of this D matrix, which is 7. So we have one equation. And the second equation is 2c2 c1 plus 4c2, which is basically equal to the second element of the D matrix, which is 5. There we go. We have a linear system of equations in two variables, c1 and c2. So there are two equations and two unknowns, so it can be solved by Cramer's rule. And if we apply the Cramer's rule here, we get c1 is equal to, we all know about Cramer's rule, it's very basic, so I am just applying it directly. So we are getting c1 here is actually 1, the coefficient is 1 here, and this is 2, and this is 3, and this is 4. And in the numerator matrix, we will get 7 and 5. So this C1 column is replaced by this 7 and 5. So I'm writing here 7 and 5. And then this second column, 3 and 4. And after simplification, we're going to get 28, 15. And then here we're getting 4 minus 6. That comes up to be 13. And that is minus 2. So we got the value of C1. In the same way, if we apply Cramer's rule for the C2, this denominator matrix will be same for the C2. So it's basically 1, 1, 2, 3, and 4. In the numerator, you will get, this time this Y or this C2 column would be replaced by 7 and 5. So the first column will be 1 and 2, and the second column, this C2 column, will be replaced by 7 and 5. And if we further simplify it, 5 minus 14, and this is going to be 4 minus 6. So this comes up to be minus 9 minus 2. That is 9 by 2. So we got the value of C2. So originally, vector D can be written. So the original equation was D was the linear combination of the given two vectors V1 and V2. And if we simply replace the values, so D can be written as 7, 5. This matrix can be written in terms of the linear combination of this V1 and V2 given matrix. So this is minus 13 by 2. So I'm just replacing C1 minus 13 by 2 times V1 plus 9 by 2 times V2. So we got our answer. D can be expressed as the linear combination of V1 and V2, these two given vectors, given that we properly scale V1 and V2 by these scaling factors or scalars C1 and C2, which are given by these two values. All right. So this was the example in R2 space. This can be, this same concept can be continued for the R3 and for the even higher dimension R4 or even Rn dimensions as well. So in that case, the number of elements of the vectors, so these elements would be higher. For the R3 case, there should be 3 components, right? 1, 2, and 3. And for the Rn, that should be n components, right? Hopefully this concept of linear combination was clear. Now, coming back to the discussion of the span of vectors. So the concept of span of vector is related to the concept of linear combination as well. They are basically related together. How? In the previous example, we saw that D can be expressed as the linear combination of V1 and V2 vectors. Now, apart from D, are there any other vectors in R2 space? So in R2 space, there are infinite number of vectors, right? Infinite number of vectors. Among those vectors, D is a vector in R2 space that can be expressed as the linear combination of V1 and V2. Now the second question is there any other vector in R2 space apart from D which can be expressed as the linear combination of the same two vectors? All right. This is a very interesting question. So apart from D, is there any other vectors? For example, is there any other vectors like Z vector, let's say Z vectors, which can be also expressed as the linear combination of V1 and V2? All right. This is another question, right? Now, given that, let's find it out. All right, let's find it out. Is there any other vectors in R2 space which can be expressed as the linear combination of V1 and V2 other than D? So in that case, we can again write down two equations. So Z can be, let's say Z is an arbitrary vectors that we are going to find out. Z x and zy. We don't know the value of zx and zy. We're going to find it out. All right. We also don't know c1 and c2 because this time z vectors we don't know. So depending on these vectors, c1 and c2 value will be different. We're going to find out. All right. Now let's write down equations for this condition. So c1 times v1 value is 1 and 2 plus c2, which is 3 and 4. This is the value of v2 is equal to the value of z is zx and zy, which we don't know, zx and zy, which we don't know. Now, if we can simplify this expression, we get like, I'm doing it directly, c1. So this is c1 plus 3c2 is equal to the first component of the z matrix, that is zx. So this is our first equation. This is third equation because we already used 1 and 2. And the second equation would be 2c1 plus 4c2. That is equal to the second component of the z matrix, zy. This is our fourth equation. Now, we have two linear system of equations, but so basically there are 4 variables, unknown variables. So this can be only solved by assuming values. For example, if we assume some values for c1 and c2, for example, c1 is equal to, you can take any arbitrary value as long as this condition is satisfied. c1 must be an element of R2. All right. As long as you satisfy these two conditions, you are good to go. You are good to take any values of C1 and C2. They should be an element in the real space. That is the two-dimensional space R2. So C1 by taking, let's say, I'm taking very simple values, let's say -1, and C2 is equal to, let's say, 1. So if I replace these two values in this equation, so we get -1 plus 3, 1 is equal to zx, which comes up to be 2. And for the second equation, if we replace the values, I get -2 plus 4 is equal to zy. That comes up to be 2 as well, right? So the value of zx and zy can be replaced by these 2 and 2. So we can write down the value of z that we just found, 2 and 2. So our original question was that, is there any vector in R2 space other than d vector, which is basically this z right now in this case, that can be expressed as the linear combination of the given two vectors? And the answer is, we found that yes, there is a vector z which is equal to 2 and 2 that can be expressed as the linear combination of v1 and v2 other than d vector. So both d vectors and z vectors, both of them is basically linear combination of v1 and v2. Only difference is that the scaling factors c1 and c2 are different for the d and z vectors. So it could be assumed, or it could be proved that there are many other vectors in R2 space, basically, which can be expressed as the linear combination of the given two vectors v1 and v2. So in that case, we just showed for these two vectors, d and z vectors, both of them are the linear combination of v1 and v2, and it could be proved as well that any vectors in R2 space that is not basically that can be expressed as the linear combination of v1 and v2, as long as v1 and v2 they are not exactly multiple of one another. So as long as v1 and v2 are not multiple, for example, if v1 is let me delete this thing. If v1 is given as 2 and 6 and v2 is given as the multiple of 2, let's say 4, and multiple of 6, let's say 12. So in that case, not all the R2 elements vector could be expressed as the linear combination of these two multiple vectors. Other than this condition, all other vectors in R2 space can be expressed as the linear combination of any two given vectors as long as they are not multiple of one another. So coming back to the definition of a span, we just figured it out that D and Z both are the linear combination of V1 and V2. So from that thing, we can construct a set which is span, let's denote it as a span, and can include all the vectors that can be written as the linear combination of v1 and v2. And this set of all vectors that can be expressed as the linear combination of any two given vectors v1 and v2 is called, this set is called the span of the given two vectors v1 and v2. So span is a set of all the vectors that can be expressed as the linear combination of any given vectors. So hopefully the concept of the dimension of the vector space and the linear combination and the span, it is discussed well, and all the confusion is clear. And if you have any question, you can put it in the comment section. Thank you very much for watching.